So now we are discussing chapter number 7, which is the electrodynamics. So what is the electrodynamics? Simply, we know that there is a charges which are at rest, and we call that physics, or that study of charges which are at rest is known as a electrostatic charge, or we call it as a electrostatic behavior. Number one, we have studied the electrostatic. Electrostatic. In this electrostatic, we have studies the stationary charges. So it means the we call it as a rho. It means it is the time independent variation. It means if the charges are at rest, the study of that charges is known as an electrostatic. The second is the magnetostatic. So now magnetostatic means the charges are in a motion, and when the charges are in a motion, as a resultant, it generates a magnetic field around it. So that magnetic field is uniform when the current flowing through the conductor is uniform. For example, let's say this is the wire, the current is flowing in the wire, it will generate a magnetic field around the wire. We call it as a magnetostatic. It means this current I is the uniform current, or the current density J. This is called the current density J, which is not a function of time. It means the electrostatic and magnetostatic both are the studies when the charge density and the current density are not the function of time. It means they do not vary with the time. It means they are the uniform. It means the charge is at rest, the charge is in motion. The motion is a uniform, we call it as a current, and the study of that current is known as a magnetostatic. It means it creates a magnetic field around it. So the study of the electrostatic and magnetostatic charges, these both gives the study of rho and J. Rho means charge density, J means current density, is not the function of time, is the time independent. It means when these are the time independent, so as a resultant, in the case of time independent, we study the behavior of the electrostatic charges, which is the charge per unit volume rho. This rho is defined as the charge per unit volume, or Q. Volume is the integral into deta. So this Q is equal to rho into deta integral. This what we have discussed in chapter number 2 of Griffith book. Similarly, this J, this is called the charge density. This is called the charge density. And this is J is called the current density. So this current density J is simply defined as the current flowing per unit volume. This V is the volume, or you may call it as a I into volume is the integral over d-eta gives the total volume. Because this I now, from this equation I, cross multiplication is equal to J into theta. So this is the behavior in which both quantities are time independent. Means both quantities are not a function of time. It means this gives rise to electrostatic current, means uniform current. This gives the electrostatic charge, means charges are at rest. So as a resultant, these both things gives the physics which we call it as the electrostatic and magnetostatic. So now where the electrodynamics is basically those charges which are not the function of time but they are the function of time if they varies with the time, which we call it as a electrodynamics. So we will look at these things. So first of all we are discussing. So now we are discussing what is the electromotive force in Ohm's law. You know that in the conductor, the force is applied on a charges. As a resultant, the charges moves from one place to another place, and we call it as a current is flowing in the conductor. It means the electromotive force is the energy or electromotive force, or we call it as a EMF. EMF, electromotive force, is called the EMF, which is the source which moves the flow of charges in the conductor when it is not connected with the source. It means this is the force which provided by the battery, or it is called the strength of the battery, which provides a force to the charge. As a resultant, the charge is moving in a conductor. If we disconnect from the electromotive force, the charge cannot move through it. So we can say that the J, the current density J, is directly proportional to the force per unit charge. So we call it as a F upon Q, or we call it as a small f. So J is equal to the small f, and this proportionality is replaced by some constant which we call it as a sigma. This constant is known as, this term is known as a sigma, and the sigma is known as conductivity of the medium. So this J is known as a conductivity of the medium. For example, this is the medium, and if this medium is connected with the source simply, so this is the medium, let's say, if this medium is connected with the battery, as a resultant, the charge will start moving in this conductor. So as a resultant, we say that the current density is directly proportional to the force per unit charge, and this proportionality constant is known as a sigma, and this sigma is known as a conductivity of the material. It means there must be a certain material inside in which the charges are moving. Material may be conductive material, material may be insulative material. If the material is a dielectric or insulator, the current cannot pass through to it and the current density J will be equal to the zero or negligible. It means the conductivity is defined as the ease with which the charges moves in a conductor, which we call it as a conductivity. And this conductivity is the reciprocal of the resistivity. Resistivity is known as a hurdle. Simply, you know that this conductivity is defined as conductivity is defined as the ease with which charges moves in the conductor. So here the charges are moving in the conductor here. Charges are moving from positive terminal to the negative charges are moving from negative terminal to positive terminal as a current from positive terminal to the negative terminal. So how easily these charges are moving, which we call it as a conductivity of the medium, which we call it as a conductivity sigma of the medium, and it is the constant property. This conductivity depends upon the nature of material. As you know that the conductivity of the copper is very good, is higher than the conductivity of iron, or the conductivity of the carbon is very low, almost negligible, because the resistivity of the carbon is higher. So as a resultant, the conductivity is one of the property of the material which shows the conduction, how the charges are moving in the conductor, which we call it as its property, and that property is known as conductivity. So now if we look here, these charges are moving in the conductor. Now these charges has a motion, has a velocity, and this velocity is under the influence of the electric field. If we disconnect this applied voltage, V or E, if we disconnect this applied voltage, the velocity of the charges is known as a thermal velocity. But when we connect it with the battery, so now battery will provide the direction to the velocity. Now the motion is not a random motion, because the thermal motion is random motion. When it is disconnected from the source, when it is disconnected from the battery, the motion of the charges is known as a random motion, is known as a thermal motion, and thermal motion is a random motion. And that thermal motion is because of the room temperature. And from this thermal motion, you can calculate easily the velocity of the charges. For example, the thermal motion is known as 3 upon 2 kT. This is known as a thermal energy. This is the thermal energy. And this thermal energy 3 upon 2 kT means 3 dimensional is equal to the kinetic energy of the charges. So 1 upon 2 mv square is the kinetic energy. V over bar gives the average kinetic energy. This means the thermal energy is equal to the average kinetic energy of the particle. This which we call it as the kinetic theory of gases. It means if we disconnect it from the battery, the energy of the electrons is known as a thermal energy. The motion is the random motion, and velocity is known as a thermal velocity. But when we connect this with the battery, as a resultant, this motion becomes a unidirectional motion. It means the charges will move towards the positive terminal of the battery. So now the velocity of the charge is known as a drift velocity. When it is connected, when it connects with the battery, the motion of the charge motion of the charges will be directional. Motion of the charge will be directional. So now such motion, such velocity is known as is known as drift velocity. Such velocity under the influence of electric field is called drift velocity. So this is known as a drift velocity, which is the velocity under the influence of the electric field. So now here, if we look here, this charge Q, this velocity v is the drift velocity. So when the charges are in motion, its velocity will generate some magnetic field. So now the total force on the charge is the electric force and magnetic force, and total force is known as Lorentz force. In this case, in this situation, the is charge is in the electric and magnetic field. The force exerts on the charge is known as Lorentz force. So this Lorentz force F is equal to Q, or charge, E plus V cross B. This can be written as an electric force, and this is called the magnetic force. So the total force is the electric force and the magnetic force. So now here, if we divide with the E, F upon E is equal to E plus V cross B. This is the force per unit charge is the small f. So the small f, J is equal to sigma into F. Let's say sigma into F, this was equation number 1. So if you substitute the value of A, J is equal to sigma, F is equal to E plus V cross B. The drift velocity is very small, so therefore this term can be ignored. The drift velocity is very small, therefore the second term can be ignored. So if we ignore the second term, the equation becomes here J is equal to sigma into E plus 0. So J is equal to sigma into E. So this is the relationship between the current density and the electric field. So the current density is directly proportional to the applied electric field, and the applied electric field depends upon the potential, depends upon the strength of the battery. So this indicates that the current density is directly proportional to the applied electric field, where sigma is the constant. It means if we increase the field means if we increase the voltage, increase the potential, as a resultant the electric field is also increased. So it will increase the current density. This sigma is known as a conductivity, and you know that this conductivity is the reciprocal of the resistivity, and this J can be rewritten as a current per unit perpendicular area into sigma, which is equal to 1 upon rho, and this rho is known as a resistivity. You know that rho, you know that the resistance in the conductor R is equal to rho L upon A. This is the very fundamental relation of the resistor in a conductor. From this equation, rho is equal to R A upon L. Substitute the value of rho in equation, let's say 3. This is equation 1. This is equation 2, and this is equation 3. Substitute this value of rho in equation 3, we get A upon I upon perpendicular area E, rho is equal to R A upon L. L goes into upward direction. A cancel. So here I is equal to, I am writing here, I is equal to E dot L upon R. So E into L is equal to potential V upon R. So V is equal to IR. This is known as Ohm's law. This is known as Ohm's law because electric field into distance is known as a potential. You know that because the potential is defined as, what is the potential? Potential is defined as the work done per unit charge. Work done per unit charge. Work is defined as the force into displacement. Displacement is length upon charge. This force is equal to Q into E into displacement upon charge. Q cancels, so the potential is equal to E into L. V is equal to E into L. So this what we have derived. We have derived the Ohm's law, V is equal to IR, from very fundamental physics that when the charges are in motion, there must be electromotive force which is to be exerted on the charges. As a resultant, the charges move from one place to another place. And we call it as the current is flowing in the conductor. The current is directly proportional to the applied electric field. Our current density is directly proportional to the applied electric field, where the sigma is a constant. So by doing some mathematical techniques, tricks, we have concluded that V is equal to IR. It means applied voltage is directly proportional to the current, or the current is directly proportional to the applied voltage, where R is the resistance, which is the constant quantity. So this is the proof of the Ohm's law from the electromotive force.